You know, in the world of AI, sometimes the most powerful, most incredible tools are held back by just one tiny hidden problem, a bottleneck. Today, we're going to talk about a billion-point problem and the absolutely brilliant mathematical tricks a few clever people used to smash right through it.
Our whole story really kicks off with this really elegant question. What if a computer could do more than just spit out a single answer? What if it could also tell us how confident it is in that answer? What if it could actually understand the concept of maybe? Well, that's the whole idea behind a super powerful tool called a Gaussian process. So, let's dive into the power of uncertainty. Why is modeling this maybe so powerful? Well, it's because the real world isn't neat and tidy with single answers, right? It's messy, it's unpredictable, and being able to put a number on that uncertainty, that's the key to making way smarter decisions when things get complicated.
Okay, I know the formal definition here sounds a little dense, but the informal idea is what's truly amazing. Instead of trying to find one single best line to fit your data, a Gaussian process thinks about a whole universe of possible functions. It doesn't just lock onto one answer, it kind of keeps its options open, which is just a much more flexible way to think. And this visualizes it perfectly. That solid line, that's the model's best guess. It's average prediction. But that shaded area, that's the magic. That's the model's uncertainty. See how it's really narrow where we have data points, and then it gets way wider where we don't? This is absolutely critical for high-stakes decisions. Think medicine, finance, engineering, where knowing what you don't know is every bit as important as what you do. So for the longest time, Gaussian processes were one of the most powerful things in any statistician's toolkit. But then, our datasets just exploded. We went from thousands of data points to millions, and now billions. And that's when a critical, fatal flaw appeared. We hit a computational wall.
This equation is the engine at the heart of a Gaussian process. And yeah, it looks a bit intimidating, but all it's really doing is scoring how well a potential model fits the data we have. And for a while, everything was great. We could crunch these numbers for reasonably sized problems, no sweat. But hiding right there, in plain sight, was our villain. This term, right here, the log determinant of the covariance matrix K. This one little piece of math is the source of all our pain. Because calculating that determinant, its cost scales cubically with the number of data points n. And this isn't just a little slow, it is a computational death sentence. I mean, think about it. If your dataset doubles, the compute time doesn't double, it goes up by a factor of 8. Double it again, and it goes up by another factor of 8. You hit that wall so fast, and suddenly you're looking at a problem that would take decades to solve. So here's the crucial insight. You don't fight this thing head on. As this great quote points out, whenever you see a problem like this, the answer isn't to just go build a bigger computer. The answer is to find a cleverer way to ask the question in the first place. Trying to calculate this directly is not just impossibly slow, it's also really unstable. There has to be a better way. And that brings us to our first heroic strategy, the approximation gambit. A team of researchers basically asked a really simple question. What if we don't actually need the exact answer? What if a really, really good approximation could be found thousands of times faster? So this team, led by Ensu Han, came up with this brilliant multi-step trick. First, they used a special kind of polynomial to create a sort of mathematical shortcut around the hard part. Then they used this clever randomized technique to get a super accurate estimate. The real key here is that this whole process just sidesteps that horribly expensive calculation and replaces it with a series of much, much faster operations. And wow, the results are just staggering. I mean, look at this plot. The black line is the old traditional method. See how its time just explodes upwards? Now look at the red line. That's their new method. It stays flat and it stays fast. It turns problems that would have taken hours or even days into something you can solve in just a few seconds. An absolute game changer. But what if you could do something even crazier? What if, instead of just approximating the problem, you could just make it disappear? Like, entirely? This is the mathematical magic trick proposed by another team, led by Louis Elam. Okay, this is just, it's beautiful. So on the left, you've got the original model with that super expensive determinant term. On the right, these researchers cleverly augment the model. They introduce a new set of carefully chosen random variables. And when they do that, the determinant from the original model and a new one from their variables, they're exact opposites. They just poof. They perfectly cancel each other out.
The problem term just vanishes into thin air.
So the process itself is pure elegance. You introduce these extra variables, which makes all the math suddenly easy. Then you run your analysis on this new, much simpler model. And then, at the very end, you just throw away the extra variables you added in the first place. What you're left with are the exact results you wanted for your original, difficult problem, and you've completely sidestepped the entire bottleneck. It's genius.
So why do we care about all this complex algebra and these clever mathematical tricks? Well, because breaking this bottleneck unlocks our ability to analyze massive, real-world data sets that were frankly completely untouchable before.
Now, we can finally apply these powerful, uncertainty-aware models to truly massive data sets. We're talking about everything from mapping crime hotspots across London using thousands of data points to creating a complete picture of the Earth's ozone layer from over 6 million variables. I mean, these are problems of immense scale and incredible importance.
So what's the big lesson here? What's the takeaway? First, as we scale up our ambitions with big data, we often have to invent entirely new kinds of math. The old tools, they just break. And second, there are often two ways around an impossible computational wall. You can either build a brilliant approximation that gets you close enough, fast enough, or you can perform a little bit of mathematical alchemy to make the wall just disappear altogether.
It really makes you wonder, doesn't it? What other huge challenges that we're facing today in science, in engineering, in medicine aren't actually impossible at all? They might just be waiting for the right person to find that one single clever mathematical trick that just changes everything.